Okay, so when we're building empirical formulas, we either need to start with the percent composition or the mass of each element. If we started with a percent, then we need to change the percent to grams. Okay, and the way we do that is we just assume we are dealing with 100 grams. Okay, because that would translate exactly to a percent. So what that looks like is if we say a compound is 40% carbon, that means we're just going to start our problem by saying we have 40 grams of carbon. Right? We're going to assume we're working with 100 grams. So if we have 40% of 100, that would be 40 grams. So the way we convert percentages to mass or to grams is that we just assume we're working with 100 grams and we just make that percent right into grams. Okay? If it's already given to us to start in grams, there's no reason to do that part of the problem. Okay? So those are the two ways that we can start. From there, you're going to convert grams to moles for every element. Okay, because the only way that we can really compare ratios of elements is in moles. We can't compare grams to grams because 1 gram of hydrogen is a whole mole, where 1 gram of silver is like 100th of a mole. Does that make sense? So comparing masses doesn't do us any good. We have to compare it in like an apples to apples type thing, right? So we have to have them both in moles in order to be able to compare our ratios. So we'll go grams to moles. Okay? Next step is going to be divide each amount of moles by the smallest quantity. Okay, and what this step does is it gives us the ratios. Okay, so you'll start to see that we can get some ratios of the amount of a substance here. Okay, there might be twice as much hydrogen as there is oxygen, which means we'd have 2 hydrogen atoms and 1 oxygen atom. Right, so we'll start to see the ratios during this step. And then the last thing that we do is build our compound. Okay, so if you want to grab out that handout that I gave you, we're going to do some of the problems. We're actually going to... What's the empirical formula of a compound which consists of 21.2% nitrogen, 6.1% hydrogen, 24.2% sulfur, and 48.5% oxygen? Okay, so we have how many elements going into our compound here? 4. And our starting amounts were given to us in what? Percentages. So what we're going to do is we're going to line them up. Our first one is 21.2%, so we're just going to put that right into grams, right? We're assuming we're working with 100 grams because all of our percentages should add up to 100. Would you agree? Okay, so we're going to just put it right into grams. So we're going to say we start with 21.2 grams of nitrogen. Okay, and we know we're going to have to convert that to moles, so I'm just going to kind of build my little mini T-chart right there. Then I'm going to move on to the next one. 6.1 grams hydrogen, 24.2 grams sulfur, and let's see, 48.5 grams of oxygen. Okay, so I'm going to convert each of these from grams to moles. So for each of them, what's going to go on the bottom of my T-chart? The molar mass. And that's going to come right from your periodic table because it's individual elements. Okay, so for nitrogens, we'd say gram of nitrogen for 1 mole. All right, we're going to do those for all of our compounds. Okay, so this is kind of our little second step. We're converting our grams to moles for every element. So go ahead and get to that part, get to that step kind of on your own. Do we see where all these numbers are coming from? This is molar mass, so it comes right from the periodic table. Bless you. Okay, do we agree with all those moles that are coming out? Anyone get different numbers? Okay, so according to your process, the next step is to divide each of those by our smallest quantity. So this will give us our ratios of sulfur atoms to nitrogen atoms and hydrogen atoms to oxygen atoms, whatever it is. So you pick the smallest one, which is sulfur 0.756, okay, the smallest number of moles, and we divide every single one by that. So one of our ratios should always come out as a 1, because you should be dividing one of them by itself, right? Does that make sense? So we'll divide each one by 0.756. And we should hopefully get really close to whole numbers, right? We should have whole number ratios. It depends on kind of where you round, but we need to be at whole numbers here. Bless you. Okay, would we agree with all of our ratios so far? Okay, they should be whole numbers. We're gonna look at what happens if it doesn't come out as a whole number ratio here on the next problem. But for this one, we dealt with all whole number ratios. So now we just build our compound. That's it. And when we build it, we usually just can go in the order that they gave us. You don't need to think about it really any more than that. But most of the time, you can just build it right in the order. So it would be N, what? N2, H, 8, S, O, 4. Yeah, S1. Well, we can leave the 1 off. That's fine. Okay. So can these numbers be reduced? There's a 1 right there. So no. Right? There's a 1 right there. So it's not going to work. Okay, and realistically, if you were getting really fancy, it would look like this. NH4, 2SO4, right? That would be a balanced ammonium sulfate, but you don't need to go that far. Does that make sense? Realistically, N2H8 is 2 different ammonium molecules, but I'm not going to make you go that far. Okay, this is where we would stop right here. Okay, but if we were really, wanting to know what the true molecule was, you could pull that 2 out, and that would balance ammonium and sulfate. Okay, does that make sense? But you can stop right here. Okay, questions with that one? Okay, so what's the empirical formula of a compound that contains 89.1% AU? What's AU? Yeah, gold. Gold oxide. Okay, so it's given to us in a percent, so the first thing that we do is put it into grams. Good. So 89.14 grams of AU. And we convert to moles. For oxygen, we have 10.8. So gold is 196.96. And we're probably good if you round that up to 197. Comes out somewhere between 0.452 and 0.453, depending on where you rounded it, which is fine. Okay, did everybody get moles in about that range? Okay, so now we've converted to moles. What's the next step? Divide by the smallest. Some of you, when you're working this, will try to stop right here and say our ratio is 0.4 to 0.6, right? That's not how it works. You still have to divide by the smallest number of moles. Otherwise, you're not truly looking at our ratio. Okay, so the smallest one is gold, 0.452. So you get 1 gold. And if you divide this by 0.452, are we seeing problems here? Comes out at 1.5 oxygen. Okay, so if we put our compound together, it looks like this, AuO 1.5. All right, can we deal with that? No. So what do you think a solution would be? What do you think? Sam? Yeah, that's right. Multiply the whole thing by 2. Okay, so that would give us AU2O3. Okay, and this is an ionic compound because it's between a metal and a nonmetal. So hopefully, we have a balanced compound here, which I think we do. But that's not something you need to be super concerned with. You should be able to just trust the numbers there as they go. Okay, AU2O3. Can we name that molecule real quick? Why don't you grab out your periodic table of ions just for some extra practice. Gold what?
3.
Gold 3 oxide. Good. So not just gold oxide, but gold 3 oxide. Good. Very good, very good. Any questions? Okay, why don't you go ahead and try the last one on that page on your own. And it says you must find the percent composition first. You can scratch that out. You don't have to do that because this one gives you the starting points in grams. So you don't have to find percent composition and then convert it back to grams. That's silly, right? Just start with the amount of grams you're given and convert to moles. You're just like skipping that first little step there. So go ahead and try that one on your own. Okay, does anyone want to give me the name for the final compound they came up with? Just the name. What happens when hydrogen comes first? It's an acid. It's an acid. If hydrogen comes first, it's an acid. So what's the name of this one? What? Which one is it? Nitric. Okay, so do we get it? HNO3? That's what we should have got, HNO3. If you take away the hydrogen, that leaves us with nitrate. Okay, so that means when you turn it into an acid, it becomes nitric acid. Anyone having trouble to get that to come out? Okay, very good. Nitric acid. All right. You can go ahead and flip to the back if you want, or go back to your notes. We're going to talk about molecular formulas here in just a little bit. There's Not a whole lot of difference, but we're going to talk about molecular formulas here a tiny bit. Okay, so if you turn to page 248, you can look at some molecular formulas. Okay, so I want you to read just that first paragraph under calculation of molecular formulas so you can get a little introduction to what we're doing here. Okay, so molecular formula differs from an empirical formula in that it's not necessarily the reduced version. This could be an actual chemical formula of a covalent compound. So it doesn't have to be reduced. It doesn't have to have a neutral charge, all that kind of stuff. So this is going to be a little bit, maybe a bigger version of some empirical formulas that we saw. So here's the thing. It gave you an example in that paragraph of BH3. Okay, this could be this is the empirical formula because it's the smallest whole number ratio of this compound. It could also be the molecular formula if we were talking about exactly this compound. Okay, but other molecular formulas for BH3 would be B2H6, B3H9, oops. Okay, and so on and so on and so on. Okay, so an empirical formula could be a molecular formula, but it's not always necessarily that they're the same. Okay? So these are all examples of molecular formulas, but this is the only empirical formula in the bunch. Okay, because it's the smallest whole number ratio. So to find our molecular formulas, essentially what we're going to do is we're going to find the empirical formula first. And calculate the molar mass. Okay. So in these molecular formula type problems, it might say this one contains 30% carbon and 40% oxygen and whatever, blah, blah, blah. And the molar mass of this unknown compound is 450 grams, right? So we'll find the molar mass of the empirical formula, and then we will divide the molar mass of the molecular formula by the molar mass of the empirical. Okay, so it's always going to be molecular over empirical. Those two could be the same, right? We could be talking about the same compound, but otherwise it should always be bigger over smaller. Okay, the molecular formula's molar mass should always be bigger than the empirical formulas unless they're the same. Okay, once we do that, we're going to take the whole number and distribute it through the empirical formula. So again, this will make sense when we look at our example. Okay, so let me just kind of talk through what this might look like. Let's say we divide our molecular formula by our empirical formula and we get 3. Right? And let's say our empirical formula was CH. Right? If I'm going to take this whole number and distribute it through, my molecular formula would be C3H3. Okay, does that kind of make sense? So if we're saying the molecular formula is 3 times as big as the empirical formula, we're going to go C3H3. Okay? That was just a quick example. The empirical formula would be CH, exactly. Okay, so let's turn to the back of your handout, and we're going to look at that first one on the back. The empirical formula of a substance is CH2O. The molar mass of its molecular formula is 180 grams per mole. What's the molecular formula? So here we already gave you the empirical formula, right? We did half the work for you. So this makes the question extremely easy. Okay, so we don't need to find the empirical formula to begin with. All we need to do is find its molar mass. Okay, so CH2O would mean 12 plus 2 plus 16. Okay, which gives us what molar mass? 30 grams per mole. Okay, and it says this molecular compound has the ratio of CH2O. Okay, but its molar mass is 180, so it's really bigger than CH2O, right? That's the ratio of it, but it's really bigger than that. So we're going to take 180 divided by 30 and get 6. Right, so now, it's given to us in the problem, 180 grams per mole. So if you look on your paper, it says the molar mass of our molecular formula is 180. So we'll always take the bigger over the smaller, okay? And we get 6. So that means the molecular formula of our compound is C6H what? 12O6. Right, that's it. So this is the molecular, and this is the empirical. Okay? Empirical is the smallest. Molecular can be a little bit bigger than that. Questions so far? Okay. Last one on this handout we're going to do in class today puts everything together. So this time we're going to build the empirical formula and then find the molecular formula from that. Okay, so we're going to start with building the empirical formula. And every one of these is given to us in grams, so we can just start with those values, right? We don't have to worry about the percentages because it was given to us in grams to begin with. Okay, so which of these is our smallest number of moles? Yeah, it doesn't matter, right? 0.116, so both of these are going to divide by themselves. Okay, so that means I got my empirical to come out about CH3O. Would we agree with that? Okay. So from that point, now what should we do? Use the molar mass. Good. We're going to find the molar mass of our empirical formula. So 12 plus 3 plus 16, which is 31. So we're going to take 62 grams per mole, which is what was given to us, divided by 31, and get a whole number ratio of 2. So now we're going to take that up here, and we're going to multiply all that by 2. So C2H6O2.